A development team spends months writing code. The automated pipeline activates, the deployment sequence triggers, and then the system grinds to a halt. In many engineering departments, leadership measures success by a single metric: the sheer volume of features shipped out the door. If code is moving, the team is perceived as healthy. But high output can mask the process failures that actively destroy engineering teams. Chronically missed deadlines, severe developer burnout, and releases riddled with bugs do not show up on a simple output tally. This standard Agile metrics dashboard outlines 8 distinct indicators tracking delivery speed and underlying team health. These panels, from velocity on the top left to escaped defects on the bottom right, provide the data points required to see past the surface level. While these metrics are often tracked individually, they are designed to function as an interconnected diagnostic ecosystem, where one data point frequently explains an anomaly in another. We are going to run a procedural autopsy on a struggling software team. By examining 3 specific failure scenarios, we can locate the exact points where their development pipeline breaks down. Fixing a failing engineering team requires leadership to look past vanity output and instead diagnose the underlying flow of the work itself. In our first scenario, a development team is consistently missing their sprint commitments. They are working heavy overtime, yet the requested features are not being finished. Panel 1 represents velocity, which tracks the team's historical capacity to complete work, measured in story points. A story point is a unit of measure used in Agile to estimate the overall effort and complexity required to implement a piece of work. Panel 2 shows the sprint burndown. This tracks the current pace of work left against the time remaining in the sprint cycle. Here is the anomaly. The team tracks the ideal trend for the first week, but then the line goes completely horizontal. A horizontal line indicates that no work is being completed. This usually implies either the work is severely blocked by outside dependencies, or the technical complexity was drastically underestimated. Relying on just velocity and burndown leaves the diagnosis incomplete. To see why the work stopped, we must look at the burn-up chart. The burn-up chart tracks work completed independently from total scope. On this chart, the team's completed work line is rising steadily, but the total scope line above it is rising at the exact same parallel rate. Because the total scope keeps increasing, the team is essentially running on a treadmill. They are completing tasks, but the finish line is actively moving away from them. The root cause isn't a lack of engineering effort. The team is failing because product management is injecting unchecked scope creep into the middle of the project. In the second scenario, features are being coded quickly, but it still takes weeks for them to actually reach the end customer. Panels 5 and 6, cycle time and lead time, reveal a hidden time gap in the workflow. Cycle time is the active engineering effort, the time from when a developer starts typing to when they finish the code. Lead time is the total customer wait time, from the initial feature request until it is actually delivered. When lead time is high but cycle time is low, it means finished code is sitting idle in an invisible queue. To find that queue, we use the cumulative flow diagram, or CFD. A cumulative flow diagram is a tool that shows the distribution of work items across different stages over time. It visualizes tasks sitting in progress, testing, and done as color bands. In this scenario, the done band remains flat, while the middle testing band swells. This swelling band is the physical manifestation of a bottleneck, typically caused by manual QA processes or cumbersome deployment approvals that prevent finished code from being released. Increasing developer speed has absolutely zero impact on customer value if the deployment pipeline is choked further downstream. In the final scenario, management forces the team to increase their velocity by 20% to hit a deadline. The development team successfully hits the target, but almost immediately following the release, critical customer complaints absolutely skyrocket. We can diagnose this by looking at panels 7 and 8, defect density and escaped defects. Defect density is the volume of bugs found and fixed internally during the development phase. Escaped defects are the failures found by the customer after the software has been released. There is a mechanical relationship between speed and stability. When velocity is artificially pushed upward, as seen on the left, escaped defects on the right often spike with a slight lag. Forcing engineering speed without quality gates simply bypasses internal testing. This doesn't eliminate the labor of testing, it merely transfers that labor to the customer, who is now tasked with finding the bugs the team was too rushed to catch. Looking at these cases together reveals the software workflow as a single, breathing organism. Speed metrics naturally coal against quality metrics, and operational health is found only when these forces are in balance. A bottleneck on the cumulative flow diagram is not an isolated event. It creates pressure that eventually forces code into the wild prematurely, spiking escaped defects. This demonstrates that metrics are most effective as diagnostics, rather than performance targets. Using velocity as an HR target inevitably invites artificial point inflation. When a metric becomes a goal, it ceases to be a reliable measure of reality. The most actionable area for improving a team's time to market is the delta between cycle time and lead time. Shrinking that specific gap allows features to reach customers faster without requiring developers to write code any more quickly. Maintaining a functional dashboard requires a simultaneous focus on both delivery and stability. Tracking delivery speed in isolation only ensures that a team will ship broken code more efficiently. Effective engineering leaders use Agile metrics not as a whip to drive teams, but as a scalpel to dissect and heal the development process.